Just imagine, in the vast expanses of space, there are planets where the sun rises twice a day and the sky shimmers with shades we can't even imagine. On these planets, mountains exceed Everest and oceans are deeper than the Mariana Trench. But the most amazing thing is that they are so similar to our Earth. With the help of the most powerful James Webb Telescope, entire new worlds have been discovered, which previously could only be found on the pages of science fiction novels. How were they discovered? In what ways are they similar to Earth, and how do they differ from us? And most importantly, when will we be able to visit them? The magical eye of humanity. The history of this incredible space apparatus began in the late 1980s when scientists were just preparing for the launch of the Hubble telescope, but were already contemplating its successor. At a historic seminar at the Goddard Institute for Space Studies in 1989, the bold idea of creating a fundamentally new telescope with a mirror over 10 feet in diameter was first proposed. At that time, no one could have imagined that the journey from this idea to a real space apparatus would take more than 3 decades. The project officially received the green light in 1996. It was named after James Webb, an outstanding NASA administrator who played a key role in the Apollo program. On NASA's official website, it is stated that thanks to his efforts, we gained our first insight into the dramatic landscape of outer space. He led our country on its first exploratory journeys, turning our imagination into reality. The initial estimates looked modest, with a budget of $500 million and a planned launch in 2007. However, it soon became clear that to realize this ambitious project, technologies that did not yet exist would be required. By the year 2000, the cost of the project had already exceeded $1 billion, and the timelines were constantly being pushed back. The main challenges arose in the creation of 3 key components: a unique segmented mirror, an incredibly complex deployment system, and ultra-precise cooling systems. The 18 hexagonal segments of the primary mirror, made of beryllium and coated with an ultra-thin layer of gold, required precision processing akin to jewelry making. The allowable surface deviation was no more than 20 nanometers. If you imagine the mirror the size of the United States, such irregularities would correspond to hills only 1.5 inches high. No less impressive was the development of the sun shield the size of a tennis court. This 5-layer structure included 140 deployment mechanisms, 70 hinge assemblies, and 400 pulleys. All these elements had to work flawlessly the first time, as there was simply no possibility of repair 1.5 million kilometers from Earth. By 2011, the project's cost had reached $8.8 billion, sparking heated debates in the US Congress. Critics called the telescope the astronomy killer, claiming that its budget was consuming funds from other scientific programs. The situation was saved by Senator Barbara Mikulski, who managed to defend the project's funding. The final cost amounted to about $10 billion. This is more than all of NASA's previous great observatories combined. In December 2021, after overcoming a quarter-century of development and testing, the telescope finally launched into space aboard an Ariane 5 rocket. The following month became the most intense in the project's history. NASA engineers referred to this period as 30 days of terror. During this time, the telescope traveled 900,000 miles, sequentially deploying all its systems. When the first test images confirmed the flawless operation of all instruments, a true atmosphere of triumph prevailed in the Mission Control Center. It was a completely deserved celebration because on the screen of every project participant were the photographs for which they had dedicated decades of hard work without any guarantee of success, which nevertheless occurred. The first discovery. In early January 2023, when Earth was just beginning a new orbit around the Sun, an event occurred 1.5 million miles from our planet that forever changed our understanding of the universe, and, most importantly, our solitude. The James Webb Telescope recorded a barely noticeable twinkling of a star in the constellation Octans, a tiny dimming that repeated with mathematical precision every 48 hours. This is how the first Earth-like planet was discovered by the newest space observatory. Scientists named it, as always briefly and clearly, LHS 475b. The uniqueness of this discovery lay not only in the fact of its detection, but also in the remarkable precision with which Webb was able to determine the parameters of the distant world. The scientists were presented with a planet with a diameter of 7,900 miles, which is 99% of the diameter of our Earth. If these two planets were side by side, the difference in size could be compared to the difference between a basketball and a soccer ball. That's how close they are in dimensions. But that's where the similarities end. LHS 475b orbits around a red dwarf, a star whose mass is only a quarter of our Sun's mass, and its luminosity is 100 times less. Meanwhile, the planet is only 1 million miles away from its star. For comparison, Earth is 93 million miles away from the Sun. Such a close orbit creates truly hellish conditions. Despite the star's coolness, the planet's surface is likely heated to 570 degrees Fahrenheit, a temperature at which lead and tin melt. The greatest interest for scientists is the planet's atmosphere. Using its near-infrared spectrograph, Webb conducted a series of observations attempting to detect traces of a gaseous envelope. The initial data turned out to be intriguing but inconclusive. The planet might have a dense carbon dioxide atmosphere similar to Venus's, but 10 times denser. Another scenario suggests the complete absence of a significant atmosphere. In this case, we are faced with a lifeless rocky sphere, eternally facing one side towards its sun. This discovery, made at a distance of 243 trillion miles from Earth, is of fundamental importance to science. It not only confirmed the unprecedented capabilities of the Webb telescope in searching for Earth-like worlds, but also gave hope for the discovery of planets with more favorable conditions. In the scale of our galaxy, which has a diameter of about 100,000 light-years, LHS 475b is literally right next door. It's like finding a person in the neighboring house when you're exploring an entire metropolis. And who knows? Perhaps this very discovery will be the first step towards answering the eternal question. Are we alone in the universe? After all, if a twin Earth planet was found at such a small distance by cosmic standards, how many similar worlds might be hiding in the depths of the Milky Way? A new solar system. But it soon became clear that the previous discovery was just a trial run for the James Webb Telescope. In the depths of space, 40 light-years away from Earth, one of the most fascinating scientific sagas of our time is unfolding. Around the dim red dwarf TRAPPIST-1, a star so small that it is only slightly larger than Jupiter, orbits an entire family of 7 planets, each of which is comparable in size to our own Earth. This remarkable system, discovered in 2017, has become the main focus of research for the new James Webb Space Telescope, which is methodically studying each of these worlds, trying to answer the fundamental question, is there a planet among them that resembles ours not only in size but also in conditions? The first in line for study was the planet TRAPPIST-1b, the closest to the star in this system. The choice was not made by chance. Orbiting its sun in just 1.5 Earth days, it offers researchers the greatest number of opportunities for observations. Although the conditions on this planet are far from Earth-like, and the surface is heated to temperatures exceeding 400 degrees Fahrenheit, making the existence of life as we know it unlikely, its study has become an invaluable training ground for astronomers. The research methodology resembles the highest level of scientific analysis. When the planet passes in front of the disk of its star, an event known as a transit, which occurs here every 36 hours, Webb's ultra-sensitive instruments detect the slightest changes in the spectrum of the passing light. In this way, scientists can accurately determine the composition of the atmosphere. If TRAPPIST-1b had an atmosphere, the gas molecules would leave characteristic imprints, specific dips at certain wavelengths. However, the initial results were unexpected. The spectrum of starlight hardly changed as it passed by the planet, as if there were no gaseous envelope in the way. This result actually has enormous scientific significance. It rules out an entire class of possible atmospheric compositions, forcing scientists to reconsider their models of planet formation. Perhaps TRAPPIST-1b is either completely devoid of an atmosphere, or has an extremely thin gaseous envelope made of heavy elements that even Webb's ultra-sensitive instruments couldn't detect. Another intriguing possibility is the presence of a thin atmosphere composed of volcanic gases, which is constantly replenished due to geological activity. The TRAPPIST-1 system continues to attract the attention of astronomers due to its unique structure and the characteristics of its planets, which open up broad horizons for the search for potentially habitable worlds. 2 planets, TRAPPIST-1d and TRAPPIST-1f, located in the so-called Goldilocks zone, are of particular interest. This region, also known as the habitable zone, is a narrow range of distance from the star where the temperature balance allows water to remain in a liquid state, which is a key element for the development of life in forms familiar to us. TRAPPIST-1e, completing a full orbit around its star in 6 Earth days, and TRAPPIST-1f with a period of 9 days, are in an ideal position to maintain moderate temperatures. Calculations show that despite their proximity to their star, these planets may possess an atmosphere capable of regulating thermal conditions and preventing extreme temperature differences between the day and night sides. If the atmospheric pressure on these planets is sufficient and the composition includes greenhouse gases in optimal concentrations, the surface conditions could be favorable for the existence of bodies of water. However, the key question remains whether there is indeed liquid water on these planets. Current research methods do not yet allow for direct confirmation of its presence. But spectroscopic observations of the planet's atmospheres in the future may provide an answer to this question. If scientists manage to detect traces of water vapor, ozone, or other biomarkers, it would be a strong argument in favor of potential habitability. Geological activity of the planets plays an important role. If their interiors remain sufficiently dynamic, this can sustain tectonic processes that contribute to climate stabilization and the cycling of substances necessary for life. However, theoretical models suggest that even in such cases, atmospheric currents can distribute heat quite effectively, forming narrow transitional zones between eternal day and eternal night, where temperature conditions may be most stable. The funding for this research alone amounts to an impressive $85 million annually. But the potential return on these investments is incomparably higher. The discovery of even the simplest forms of life would be the greatest scientific breakthrough in human history, comparable only to the discovery of the New World or the deciphering of the DNA structure. Even now, these studies are fundamentally changing our understanding of planetary systems and the conditions for life in the universe. And although the first studied planet of the system, TRAPPIST-1b, turned out to be a lifeless, scorching world, its six sisters continue to hold their secrets, which the James Webb Telescope is methodically unveiling, step by step, bringing us closer to answering one of the most fundamental questions. This scientific odyssey is particularly impressive when you consider that just a few decades ago, we didn't know of a single planet beyond the solar system. Today, not only have we discovered thousands of exoplanets, but we also have the ability to study their atmospheres and surface conditions in detail. The TRAPPIST-1 system, with its 7 Earth-like worlds, has become a kind of cosmic laboratory where our theories about planet formation and the emergence of life are tested. What is it ultimately? Persistent attempts to find other life or a race against the unknown that humanity has learned to conquer. It is both far and near at the same time. Undoubtedly, we have learned to explore and analyze the most distant celestial bodies, despite the vast distance. But if we seriously think about it, what do these spaces represent? How surmountable are they and how close are they? 40 light-years is a distance that both fascinates and sobers. On the scale of the Milky Way, whose diameter is about 100,000 light-years, the TRAPPIST-1 system seems like our closest neighbor. If we imagine the galaxy as the size of a football field, this red dwarf would be just a few steps away. But in familiar earthly measurements, this distance turns into a staggering 240 trillion miles. A journey for which humanity would need to undergo a true technological revolution. Current spacecraft make this task impossible for now. Take Voyager 1 for example, the fastest human-made object, hurtling through interstellar space at a speed of 38,000 miles per hour. Even at such an incredible speed, it would take about 740,000 years to cover the distance to TRAPPIST-1. That's 25 times longer than the time since the first cave paintings appeared, in the Lascaux caves. But scientists and engineers around the world are already working on technologies that could reduce this journey to the span of a human lifetime. The most realistic project today appears to be Breakthrough Starshot, an ambitious initiative costing $100 million. Their concept involves creating a fleet of microscopic probes weighing only a few grams, equipped with ultralight light sails. Powerful laser arrays on Earth could accelerate these tiny devices to 20% of the speed of light, about 134 million miles per hour. At such a speed, the journey to TRAPPIST-1 would take approximately 200 years, and although the creators of the probes themselves will not see the results of their work, their great-grandchildren could receive the first photographs of another planetary system. But these are only photographs, not a manned flight with a crew, but simple images at the cost of 200 years. More ambitious plans include thermonuclear pulse engines, where a series of controlled thermonuclear explosions accelerates the ship to 20% of the speed of light. Such a mission would require trillions of dollars from international cooperation and, in theory, could deliver an automated station in 350 years. For manned missions, scientists are developing even bolder concepts. The ICAR project, bringing together the best engineering minds from around the world, is exploring the possibility of creating thermonuclear engines capable of accelerating a spacecraft to 10% of the speed of light. Such ships, comparable in size to modern aircraft carriers, would become true generation arcs. Self-sustaining ecosystems where dozens of generations of space travelers would pass before their descendants reach the destination. The cost of such a project is estimated to be in the hundreds of billions of dollars, comparable to the annual budget of a small country, but quite realistic for future international cooperation. Against the backdrop of these distances, Mars, located on average 140 million miles from Earth, which is 18 million times closer than TRAPPIST-1, seems like a more attainable goal. However, even such a distance remains a colossal challenge. A modern flight to Mars takes about 9 months one way and costs around $100 billion. The main obstacles, printain, are the radiation of the Van Allen belts and the need to use 850 tons of fuel for the mission's return. This is 30 times more than what is required for the entire lunar program. For comparison, if a journey to TRAPPIST-1 is like trying to surf across the Pacific Ocean, then a flight to Mars is akin to rowing across the English Channel, challenging but fundamentally possible with current technologies. Paradoxically, it is the study of TRAPPIST-1 that helps solve Martian challenges. The spectrographs developed for Webb are now searching for water in Martian canyons, and life support systems for hypothetical generation ships are being tested at Antarctic stations. Interestingly, even if humanity is never destined to physically reach TRAPPIST-1, the study of it is already changing our understanding of the universe. When we analyze the composition of the atmospheres of these distant worlds or measure their temperature, we are essentially creating a guidebook for future generations of explorers. Perhaps in a few centuries, schoolchildren will memorize the names of the TRAPPIST-1 planets just as they learn the continents of Earth today. These worlds, so distant and yet strikingly familiar, present a unique challenge to humanity. On one hand, there is the technological challenge, how to overcome 40 light-years when even the journey to Mars remains a formidable task. On the other hand, there is the philosophical challenge. What does the potential discovery of life around another star mean for us? But even today, looking at the data from the James Webb, we can feel like part of something grand. And even if it turns out that there is no life in the TRAPPIST-1 system, its very existence proves that there are countless Earth-like planets in the galaxy. Once, our ancestors looked at the ocean, dreaming of what lay beyond the horizon. Today, we look at the twinkling of a red dwarf 40 light-years away and dream of new worlds. The difference is only in scale, but the essence of human nature remains unchanged. We are always drawn to what lies beyond the reachable.